All right, folks. So in today's video, we're going to talk a little bit about ham radio antenna basics. We're going to cover a intro to a bunch of topics. So by the end of this video, you should be able to understand a little bit more about ham radio antennas if you're a beginner, and you'll be able to speak to folks about your antennas and understand how you want to use antennas moving forward. We're going to begin the conversation by talking about antenna tuning, because this is something that you'll have to do regardless if you buy, build, assemble a kit, whatever kind of antenna that you're going to use. Once you install or erect that antenna, you're going to have to tune it. What I have here is hams often need to adjust or modify antennas to optimize performance on desired frequency. And so that means that your antenna has to be tailored to meet the needs that you have for the bands or the frequencies that you're going to operate on. They tend to use SWR, standing wave ratio, or VSWR, sometimes pronounced VSWR, as a metric for evaluating antenna performance. VSWR is just SWR with a V on the front of it, standing for voltage. The act or the art of antenna tuning includes adjusting the size of the antenna, the location, the height, and using variable tuners as well as matching devices. So there's a lot of different things that you can do to tune or adjust your antenna to perform more optimally than if you didn't tune it. Hams will also design or modify antennas using reactive components that improve performance. And we'll take a look at an example of that towards the end of this video. Have you heard? PCBWay is having their 5th PCB design contest. Let's check it out. PCBWay's contest starts on September 1st and runs through December 31st for release time. The project review time goes from January 1st to January 31st, and the announcement is made February 6, 2023. The rules are simple and easy to follow. Go ahead and enter and take your chance on winning some of these great prizes. You can do this at PCBWay.com. Okay, so next we're going to talk about SWR or VSWR. Here I have it's more correctly referred to as VSWR, but that's not important. If you say that, people will look at you weird and they're going to expect you to say SWR in the ham radio or amateur radio community. It is a measurement of impedance match between a transmission line and a load, in our case an antenna. SWR is expressed as a ratio. So for example, 2:1 is a common SWR measurement or ratio that you'll hear, and this means that you have 100 ohms of impedance on your load to your 50 ohms of impedance on your transmission line. So a couple things to pay attention to. An SWR of 2:1 is roughly 11%, 11.1% to be more precise, of your power being reflected back towards your source or towards your radio. A transmitter operating at 100 watts into an antenna will only have 89% or 89 watts of its forward incident power absorbed by the antenna. And we say absorbed, it can be either dissipated in the antenna as ohmic resistance, or it can be radiated as your signal. So that's antenna efficiency. So there's a couple things that we want to make sure that we understand here. We're talking about impedance, and I have a video that I'll link below that explains the difference between resistance and impedance. So let's talk a little bit about the impacts of SWR and make sure that we understand what's happening. So if you're operating at 100 watts and your coaxial cable has 1.25 dB or decibels of line loss, only 75 watts is reaching the antenna. Now I have a video on line loss, and I'll include that below so you can check that out. But what is important to understand here is that at certain frequencies, your coaxial cable can attenuate your signal to a certain degree. We measure this attenuation in terms of decibels or dB. In this case, in our example case, we're losing about 1.25 dB, which is about 25% of our forward power. So only 75 of our original 100 watts are reaching the antenna. If we take a look further down in our example, we talked about an SWR of 2:1, which reflects about 11% of our power back to our radio. So when you take into account your 75 watts times 11%, that is 8.25 watts being reflected. And this means that about 66.75 watts are being transmitted out of your original 100 watts. Now, there's some folks that'll tell you that you should use transmission line that's less lossy, like ladder line, for example, or high-quality coaxial cable. That's a choice that you're going to have to make based off of your budget and your installation location. The other thing that you'll hear hams say is that That reflected power is not lost. It's bouncing back on your cable. And once it goes back to your radio or your tuner, it will be reflected back towards your antenna. But you're going to lose that power, again, in terms of your 1.25 dB in line loss. So there is loss due to ohmic resistance, and that's something that you should consider. This slide will make people's eyes glaze over, but it doesn't have to. So one of the things that we need to do when we are putting up an antenna is we need to make sure the antenna is sized correctly. And you can sometimes add to your antenna or you can remove from it. In the case of a wire antenna, you can add another piece of wire to the end of your element, or you could trim some off. And I just wanted to throw this in here so folks are aware of it. This is part of the test that you'll have to pass in order to be a licensed amateur radio operator. But when we talk about the size of the antenna, there's a couple of different variables that we have to consider. Frequency, the length of your antenna, and then the element length. In a dipole antenna, for example, and that's the example we're going to talk about mostly in this video, you have two elements, one on either side of the antenna. That's why you have di for two and then pole for poles. The total length of your antenna is the sum of those two elements. So if we take a look at the formula, what you see here is the length of your antenna should be 468 divided by the frequency that you want to operate on. The elements of your antenna on your dipole should be the length that you come up with from the formula divided by 2 because you have two elements. So the example that we have here, our length is 468 divided by 14.200 megahertz because we want to operate on the 20-meter band. So each element would be the 32.957 feet divided by 2, and that gives me an element length of 16.478. Now, not all wire is created equal, so when I build this antenna, I have to take into consideration things like velocity factor. So what I typically do is if I build an antenna, I make sure my element length is a little bit long. And most antennas on the market will come this way. That way you only have to remove, and do it cautiously, a little bit of your antenna as you're dialing in your SWR, tuning your antenna for optimal performance. I'm blocking portions of the screen, so I'm going to turn myself off. What we have here are called far-field plots, and they allow us to take a look at a model of our antenna and anticipate how it will work in real-world conditions. Each one of these far-field plots has a data table that gives us certain pieces of information. This can get complex and overwhelming, so we're not going to talk about all of it. But what I wanted to mention is the far-field plot on the left is of a dipole antenna that is mounted 10 meters above ground. For a 20-meter dipole, we want to mount it 10 meters above ground because that is half of a wavelength, and that is the desired height for mounting this antenna. So when we take a look at this, we see an SWR of around 1.7, and folks might say, well, holy heck, what's going on there? So if we look at the plots, each one of these has two diagrams. The one on the left is if you were looking down upon your antenna and you were seeing the radiation as it leaves your antenna. So you can see here, north and south, we have more gain or more directionality of our signal. If you look on the right-hand side of the far field plot, you'll see a horizontal elevation where if you're looking at your antenna from the ground and you were able to take a slice of your radiation pattern at its most dense point, you can see the takeoff angles. So on the left-hand side, what it looks like is if you had maybe a capsule sitting on the ground and you took your finger right in the middle and pushed it down and squished it. And then what you would get is these expanded lobes on either side. That is the way that your signal will radiate when you have your antenna mounted 10 meters above the ground. And you can use the angle of trajectory coming off of that to anticipate where your signal will be the strongest and how that will propagate against the ionosphere. If you take a look at the antenna on the right, you can see when you're looking down upon the antenna, it's a little bit more squished in the center, but you still have north and south being the direction of your antenna's strongest signals. On the right-hand side of that, you can see a much different pattern or takeoff angle here. You can see a large lobe going straight up in the air. Now, this antenna, again, is a 20-meter dipole, and it is mounted 15 meters above ground. So that is 3/4 of a wavelength high. One of the things that you need to be careful of is a lot of times ham radio operators get tribal think, and they'll say things like, height is might. Get that dipole as high as you can, son. Get it in the air. Height is might. Well, in this case, you have a lot of energy that is going to go straight up into the ionosphere and is not going to reflect anywhere and is not going to get you good contacts. Now, an argument can be made for near vertical incident skywave. There'll be another video on that, so I'm not going to get into it. But you can see the left and right lobes as they project out are smaller than the ones on the antenna mounted at 10 meters. And as a result, you have less energy, less signal, and less chance of making a contact going out. But what I wanted to talk about was this antenna mounted at this height has an SWR of 1.4. So traditionally, when you think about SWR, folks want to be closest to 1-to-1 ratio. They want to get further and further away from the 3-to-1, 2-to-1 that we talked about, and get to a 1-to-1 ratio. Well, to an untrained person, they would say, well, 1.4 is better than 1.7. I'm doing a better job mounting and tuning my antenna. But the question comes up, are you really? Because the bulk of your energy is going to be radiated vertically into the sky. Folks will call that a cloud warmer, and it's not going to get you the results that you're anticipating. Here's a real-world example of some tuning I did on an antenna that I built. This antenna was an end-fed half-wave dipole. It's just like a dipole, except for you feed your coaxial cable into one end of the wire. And the blue line in here depicts my initial installation of the antenna, and then after trimming the antenna, what happened is that I got closer to the resonant points that I wanted, and that is depicted in the orange or the red line. Now, what you can see here, the gray bars represent the frequencies for the ham bands, and initially my antenna was a little too long. So when you look at a tool that will allow you to plot your antenna, this was done on a nano VNA, but there are other tools on the market. What you can see if your antenna is a little bit long is that your dips or more resonant points are going to be to the left of the frequency that is desired. If it's too short, they're going to be to the right. So because my antenna was long and I trimmed it shorter, my dips shifted to the right, getting it a little bit closer to where I want, but not exact. So what we talk about with antennas sometimes is the Q factor of an antenna. Some people say it's extremely valuable metric. Some people say it's not. I do have a video that explains Q in more detail than we're going to cover here. But what you need to think about is your antenna broadband or not? When you have an antenna that is closer to resonance across a wide spectrum of frequency, it is said to have a lower Q. When it is only near resonant on a smaller portion of frequency, you would say that it is high Q. So in this picture that I drew, the red line represents a lower Q antenna. And what's handy about that is that I can use that antenna across a wider span of frequencies without having to adjust my manual tuner or adjust my antenna in any form or fashion. But this makes my antenna less efficient and comes at a cost. Because it's closer to resonance on more frequencies, it's more susceptible to noise and interference from other adjacent frequencies. If you take a look at a high Q antenna, your spectrum is much more narrow, and you can see that here depicted upon the blue line. High Q antennas tend to be a lot more efficient, but require a lot more adjustments and tuning as you use them, especially if you jump around on the bands a lot. I don't know about you, but I change frequency all the time, so I tend to use low Q antennas, and I'm willing to make the compromise of efficiency in order to do that with less hassle. Once again, I'm blocking portions of this slide, so I'm going to remove myself from the video. Now, I threw this slide in here because a lot of times you'll hear folks say that they use resonant antennas, or they only want antennas that are resonant. They know that their antenna is resonant, so they don't need to use a tuner. What I don't see a lot of folks do is talk about using a Smith chart or understanding the reactive components. We talked about this a little bit when we discussed impedance earlier of their antenna to really understand what is going on with their antenna. So an antenna is resonant when there is no reactance. You have only purely ohmic resistance. When we talk about reactance, we talk about induction and capacitance, and these are two characteristics that you'll see as part of your impedance makeup. So when we take a look at the Smith chart, you see on the equator line, that is where your antenna would plot if it was resonant. If it plots above or below that line, it's not resonant. So if you look carefully on this slide, there is a point to the left-hand portion of the Smith chart on the equator. And point A is actually resonant because it is on that equator. Now, equator is not the right term, so don't get upset at me, but I am thinking about my target audience here. So at point A, we have a 5-to-1 SWR, and people will say that 5 SWR, well, this antenna is not resonant. Well, it is resonant. You're not considering the fact that it doesn't have inductive or it doesn't have any reactive components. If you take a look at point B, which is close to the 12 o'clock position pointing straight up, the antenna is not resonant, and it has an SWR of 2.44 to 1. Well, that's nearly half the SWR of point A. So somebody would say, oh, look, this antenna is more resonant. Well, it's not. It's better matched. That's important for folks to understand that. I'm not advocating one is better than the other. What I am advocating is education and making sure that you understand how your antenna is performing and why it is performing the way that it does. When you take a look at point C, that is on the equator again towards the right-hand side of the Smith chart. And you can see that there's an SWR 4-to-1. I want to thank the ARRL. I used this image from the 24th edition handbook, so I wanted to give some attribution for that. So this is an antenna that I put together that I just love, and I talk about it all the time on my channel. I do have video on this antenna, so I can include that link below. This is an antenna that I call the Shorty 40, and there's a couple of different components here. Earlier in the video, I mentioned that folks will add devices to their antennas or components to their antennas to adjust the reactance that we've been talking about. And here I have an induction coil that I have about 2/3 of the length of my element. What this induction coil does is adds inductance and makes my antenna look electrically longer. This antenna is an end-fed half-wave dipole, and it's about 42 feet long. This antenna without an induction coil is about 66 feet long. So I built this antenna because I had to mount it in a smaller space and I needed the antenna to be shorter. So what I did is I added that induction coil. Now that does come as a little bit of a compromise because I would get better performance out of a straight long wire antenna. Now in the blue box, we have what I would call a unun. Now that stands for unbalanced, unbalanced. We're not going to get into all that. Some people would call that an impedance matching device or an impedance transformer, and or they even call it a matchbox. But we're just going to call it an unun for now. But at the bottom part of that toroid, you can look carefully and you'll see a little blue capacitor. Well, that capacitor adds capacitance. And what that allows me to do is operate this antenna on lower frequencies by adding capacitive reactance. We're going to take a look at a chart that shows how this works. But we talked about antennas being longer electrically and shorter electrically during the tuning phase. What we've done with this antenna is we've made it look longer than it really is with the induction coil, and we've made it look shorter than it really is with the capacitor. So let's talk about the capacitor. And what you can see here is a graph. The blue lines, light blue lines, depict the ham bands, and what you see with the red line is a sweep I've done from 40 meters down to 10 meters of the antenna, of the unun without the capacitor. And so what you can see is you can see my SWR, my standing wave ratio, go up the higher in frequency that I go. Well, that's not what I wanted. I wanted it to be lower. So what I did is I added that capacitor, and then the results are the blue line that you can see below, and that keeps my SWR a lot flatter. It doesn't make my antenna any more efficient. What it does is it tricks my radio into thinking there's a better impedance match, and I don't have to worry about reflected power. It's all going to the antenna. Now, what happens in that antenna might be a different story. So I mentioned before that with amateur radio, and when we make adjustments to our antenna and we choose an antenna, we make compromises along the way. So what we have here is my Shorty 40 antenna as it's mounted in its location, and I have a couple of data points here. The red line is my final measurements of SWR when I had the antenna tuned in the way that I want it. What I wanted to talk about is that my antenna has high and low Q at different frequencies depending upon the behavior of the reactive components that I've added. So at the 40 meter band where the blue arrow is, you can see a very steep V. And that is my resonant point, or my near resonant point, as I should say. And what we see there, it's very high Q, and that is a result of using the induction coil. When we play trickery with our antennas to make them feel like they're longer than they really are, you narrow your Q. You can see that my near resonant point on 20 meters, where the red arrow is, spans across the entire band, and that would be considered very low Q. High Q with blue, low Q with red. Anyhow, I hope that these concepts have helped out and maybe explained a little bit more about antenna basics and understanding how they work. If you have any questions, comments, suggestions, or recommendations, go ahead and post them below and I'll do my best to respond. Thank you.